Wel, croeso cynnes iawn I chi noswaith dda. Mae'n braf iawn cael eich cwmni chi heno. Thank you for joining us this evening. Delighted that you're present for this webinar. My name's Damien Walford-Davies. I'm Deputy Vice-Chancellor at Cardiff University, and I'll be hosting tonight's event. An event on the subject of delivering the technologies for net zero. And just to say that this evening's digital showcase, call it that, will be recorded, as you've just heard, and we will send you the recording link following the event, and you're welcome to share that link in addition. A few comments from me before I introduce this evening's speakers. I've just finished reading David Wallace Wells's book, The Uninhabitable Earth. And it was a hell of a read, a book the Canadian writer Margaret Atwood called urgently readable. Some of you may know it. It's an account of a climate emergency that offers two things, really, both a rigorously scientifically informed analysis of the causes and the impacts of global warming, and a sobering, imaginative summoning, if you like, of the punishing effects of doing nothing and continuing to, as the author calls it, weaponize the environment. It is the greatest challenge we've faced, and Cardiff University is assisting to tackle the issue by delivering new technologies and studying actually the human behaviors that both contribute to and mitigate that huge problem. So we are responding, and we're doing so by investing, as you can imagine, in researchers, in the human capital, and in research facilities and infrastructure that will deliver solutions. Our Translational Research Hub, a 129,000 square foot state-of-the-art facility co-funded by Welsh and UK governments, opened this year. And that houses the multidisciplinary teams of scientists and engineers who work within our newly established Net Zero Innovation Institute to provide those solutions that I've just been talking about for a sustainable future. So tonight's event showcases that contribution, those people, and that institute. And I'm delighted to welcome our speakers, Professor Duncan Wass, Professor of Catalysis and Director of the University's Net Zero Innovation Institute, and Dr. Jennifer Edwards, Senior Lecturer at the Cardiff Catalysis Institute within our School of Chemistry. So the order of the evening, a few brief housekeeping comments here, is as follows. We'll hear from Jennifer and from Duncan shortly, and then tonight, as the audience, you'll have an opportunity to ask questions and I'm sure receive persuasive answers. We've already received some questions in advance, and I may begin with those. But for those questions as yet unasked that will be generated by what our speakers say tonight, please enter them in the Q&A box at the bottom of your screen, and we'll attempt to answer as many as time permits. But for now, that's enough from me. I'm delighted to ask Duncan, followed by Jennifer, to present. Croeso, welcome, Duncan.
So thanks very much, Damien, for that introduction. Good evening, everyone. I agree with Damien that of all the problems facing the modern world, climate change is the most serious and the most urgent. I also believe that it's a sign of progress that this problem is now so well known that I don't need to spend time this evening convincing you that there is a need for action. So what action is needed? Well, here the language can be confusing. Do we need net zero? Do we need to be carbon neutral? Do we need a circular economy? Do we need to be sustainable? People often use these terms as synonyms. In fact, they do mean slightly different things. I think the most useful term here is net zero, and it's useful for two reasons. Firstly, and pragmatically, this is the phrase that government and larger organisations tend to be using. I think secondly, though, and more importantly, I find it quite a positive, optimistic term. Net zero is the solution to the problem. It's not the problem itself. If we can achieve net zero, we do have a route out of this. At this point, it's probably useful to define what I mean by net zero. And And perhaps surprisingly, there's not one internationally agreed definition of net zero. I think a useful definition for this evening would be that net zero is the point when greenhouse gas emissions into the atmosphere are balanced by the removal of greenhouse gases from the atmosphere. Straight away, that presents two possible extremes. One extreme is that we just carry on emitting carbon as we do now, but we mitigate that by removal of the carbon with, for instance, carbon capture technology. The second extreme is that we don't emit any greenhouse gases at all. Of course, the reality will be a balance somewhere in the middle of those extremes, although I should add that it's somewhat easier not to emit the carbon in the first place than it is to clean up afterwards. There's also sometimes an assumption that the route to net zero is clearly mapped. That's not the case. Certainly, some of the technology that we have for net zero is available. Zero carbon electricity from wind power, for instance. But it's not simply a case of having the will to adapt and use the technology we already have. Part of the route to net zero is simply not mapped yet. It's terra incognito that we need to fill with new innovation. And of course, that innovation is where Cardiff University can come in. So we're going to be launching the Cardiff University Net Zero Innovation Institute. This builds on the internationally leading research we have in the university in many aspects of research related to net zero. And you can see some of them on this slide. I'd highlight here that although we have a real strength in the physical sciences and engineering, so things like catalysis that I will talk about later and compound semiconductors, we also have great strength in the social sciences. And bringing together the physical sciences and social sciences is crucial in this area. Policy needs to be informed by the new technology that's coming on stream. And that new technology needs to be informed by human behaviors, how people will adopt that new technology. We also need to go beyond the traditional university focus of just having discovery research. We need to translate that research through innovation into real applications. And this is something we need to do in partnership with funders, in partnership by collaboration with other universities, and crucially, in partnership with end users, in particular industry. So I'm going to focus now on my area of expertise, which is catalysis. And a good place to start is maybe another definition. So anybody that's studied any catalysis at any point in school will maybe be familiar with these definitions. Catalysis is the acceleration of a chemical reaction by a catalyst. A catalyst is a substance that increases the rate of a chemical reaction without itself undergoing any permanent chemical change. Now, these are rather dry textbook definitions, and what they don't really give a sense of is the importance of catalysis. Chemical reactions are responsible for all of the materials around us in the modern world. And so if a catalyst can speed up and control chemical reactions, this is the most powerful technology we have for making new molecules. And that power is realized already through, for instance, the petrochemical industry. Some 80% of all of the chemical processes we have use catalyst technology at their heart. Now, traditionally, that catalyst is used for converting a building block that we will dig out of the ground, like gas or oil, into a more valuable material, such as a plastic or a fuel. But we can also use catalysts to convert things like waste or sustainable feedstocks or carbon dioxide into more useful materials. And these are the types of catalysts that we're researching in our institute. I should add that catalysts, as well as being very good at making molecules, are also very good at destroying molecules. And this is also an important application to take harmful materials and to make them benign with a catalyst. And perhaps the most widespread known use of a catalyst would be a catalytic converter in a car. And that's exactly what they do. They take some of the harmful gases and turn them into something more benign. But the case study I'm going to give you this evening is concerned with liquid fuels. So things like kerosene, petrol, and diesel. We have an insatiable appetite for these liquid fuels. If you look at the world consumption of liquid fuels and you divide that by the world population, you come to a figure of burning 2 litres of liquid fuel for every man, woman, and child on the planet every day. That's a huge amount of carbon we're burning and clearly unsustainable. Now, there are various solutions to this. Electrification is one, so going towards battery cars, but it's only part of the solution. We need a portfolio of solutions. And another important technology in this area is to use biofuels. So rather than having fuels which we dig out of the ground, to have fuels which we can grow. Now, this is an area that has some controversy. There are debates about using crops that could be used for food and using them as fuel, and clearly there are issues with biodiversity. So we need to be very careful that the crops here are grown in a sustainable way. But if we can grow sustainable crops, then this can be part of the solution. So when people talk about biofuels, they tend to mean 2 things. On one hand, there's biodiesel, and that's largely a solved problem. On the other hand, we have biopetrol, and that is more difficult. So you've probably noticed in UK forecourts, the standard petrol now is called E10. So this means that it's got 10% of bioethanol blended in with the standard petrol, and that makes it a more sustainable material. But actually, ethanol itself is not a great fuel. So here's an ethanol molecule. This has problems. Its energy density is rather low compared to petrol. It's a little bit corrosive, and 10% is the maximum sort of blend ratio you can have. A far better sustainable biofuel is butanol. Quite simply, this has 4 carbons in it rather than 2 carbons in ethanol. So this burns very much the same as standard petrol. You can blend it to a much higher ratio. The problem is how we make butanol. There are fermentation routes to make this, but tend to have very poor selectivity. So that means that we do make some butanol, but we make lots of other things that we don't want as well. So we have this problem. Butanol is a very good fuel, but very difficult to make. Ethanol, less good as a fuel, but since antiquity, we know how to brew things to make ethanol. So a solution to this problem is where catalysis can come in. Maybe we can develop a catalyst which will convert ethanol into butanol. It speeds up the chemical reaction of upgrading ethanol into butanol. Well, this looks very simple to put on a slide. Actually, it turned out to be very difficult to do in practice. I've just got one slide with a bit more technical detail here for anybody with a more chemistry background. So this was the solution to the problem. I think, interestingly, this is a very old chemical reaction, the Gerbe reaction, over 120 years old. And we've managed to repurpose this very old reaction for a very modern problem. Here's a picture of our catalyst. This turns out to be an extremely good catalyst. So over 94% selectivity to make butanol, which is the material we want. You can see this catalyst is based on the metal ruthenium, chemical symbol Ru. And the important part of the catalyst here is actually this framework that you can see around the ruthenium. This is what took us a lot of time to design. And it's this framework that makes the catalyst very selective to just make the butanol molecule that we want. So we're very excited about this result. This, at the minute, is the world's best catalyst for making what could be petrol in the future. And of course, you know, that could be very significant. But turning this into commercial reality is something that will require partnership. And we're working with industry partners to develop this. So in my short presentation this evening, I've given you a background to some of the net zero research going on in Cardiff University. I've introduced catalysis and why this is such an important technology to deliver net zero, and given you one case study of how we can use catalysts. And now I'm going to hand over to Jenny, who's going to give you a very different case study in using catalysis and show just the breadth of importance of this technology in meeting net zero targets.
Okay. Damien, I'm hoping everyone can hear me okay. Damien, thank you very much for that very kind introduction. And Duncan, thank you for so nicely sort of introducing the topic, and that provides a great background for the work that I'm going to share today. Okay. So in terms of definition that we have for net zero, I took a definition from the United Nations website. So this means cutting greenhouse gas emissions as close to zero as possible. Now, the terms that are in that definition, things like greenhouse gas emissions, we've been talking about carbon dioxide, often lend themselves to us thinking about net zero being a thing that industry needs to address. Okay, so here's a picture of a coal-fired power station with multiple chimneys belching out huge amounts of CO2. And as individuals and individual households, the way in which we can contribute towards achieving net zero and reducing carbon emissions can seem to be quite small. And what I'm hoping to do today is sort of show you about how we can sort of think about a household contribution towards net zero as being very important. Okay, so this is quite an interesting article I found on the BBC, which was published a couple of years ago. And this sort of article kind of gives sort of a good background to the way in which we as individuals can think about addressing net zero and emissions. And the particular part of net zero that this sort of addresses is water and the way in which we use water within the household. Okay, and I'd highly recommend looking at this article. Okay, and essentially they cited some research done by WaterAid, which looked at the water use and the carbon costs associated with that. And the focus I'm going to have here is on washing machines. So in an average household, a washing machine uses around 38 litres of water per day, and this has an inherent energy cost. So of that energy cost and the CO2 produced, around about 80% of the energy used and the CO2 produced there is in heating the water, and the hotter a wash you do, the more CO2 you're going to generate. And around 20% is from using purifiers, so the purification process of the water as it comes into the house and the chemicals that are involved. Now, we also have a lot of research going on within the Cardiff Catalysis Institute on water purification, but that's not actually the topic I'm going to cover today. So in all, around 118 kilograms of CO2 are estimated to be produced per house per year just from using the washing machine. And as research scientists, okay, we have academic freedom to kind of think outside the box here. So there's a lot of work done with the water community. We're thinking about metering and reducing the amount of water that goes to households and the amount that we're using to bring down CO2 emissions, and more efficient washing machines, for example. But as academics, we kind of think outside the box occasionally, and we think, well, is it possible to actually wash clothes without using water? And this is what I'm going to discuss just now. Okay, in March 2020, just as COVID hit, the Bill and Melinda Gates Foundation had a funding opportunity in this area, and they fund a lot of humanitarian work. Okay, and the funding called for innovations in material scientists. And so as a catalysis person, I also have an interest in material science, and they were looking for innovations in material science for a transformative menstrual health and hygiene product. And the aim of this is to improve the reproductive health in low and middle income countries. So by their own requirements, they were looking for a transformative product that wouldn't require clean water or result in waste. So period poverty is a huge global challenge, doesn't just affect low and middle income countries, it affects all countries. And this is quite a horrific statistic in that it's estimated that 582 million people lack what they need to adequately address their menstrual health care. So given that particularly for people in low and middle income countries, the cost and availability of disposable products is prohibitive. And so when reusable products tend to be used, if washing facilities are quite poor, the use of unsanitary items can really have negative health consequences. Okay, so it can cause urinary tract infections, bacterial vaginosis, suffering with one of those conditions when pregnant can lead to miscarriage, and also toxic shock syndrome and sepsis. Okay, so we had the thought of, can we use catalysis to address this and put in a proposal for the bid for this round of funding. Okay, and catalysis can. So the type of catalyst we were thinking about using here is a photocatalyst. Okay, and the definition of that is a material which is typically a semiconductor that changes the rate of a reaction on exposure to light. Okay, so this is going to get very slightly technical just for a second. Okay, so I have a cartoon here of a photocatalyst, and essentially what happens is on irradiation with light, the photocatalyst, the powder, the solid, becomes excited. And this excitation manifests itself in a charge separation within the photocatalyst, and you end up with a negatively charged domain and a positively charged domain within the photocatalyst. Now, the negatively charged domain can undergo a reaction with oxygen in the air to form superoxide radical. And the positively charged domain can react with water. So this could be in solution, in aqueous solution, or if it's in air with any moisture within the air. Okay, and that causes the water to turn into hydroxyl radicals. So perhaps for the purposes here, we can think about a photocatalyst as being a substance that uses light to generate highly reactive oxidizing species, which are free radicals. Now, free radicals tend to be something that we try to avoid because they're highly toxic to cells, okay, and they can cause cell death and cause cancer and various other things. Okay, but for the same reason that our cells are susceptible to them, so are bacterial cells and other microbes. So our scientific question was whether we could incorporate a solid photocatalyst into the top layer of a reusable sanitary towel that self-cleans in sunlight without the need for water. And we can just think about the oxygen in the air to form those radical species and perhaps any moisture in the air as well. Okay, so the targets that we set ourselves for this, so the catalyst textile hybrid should have excellent antimicrobial activity, it should have deodorizing activity, and it should have destaining activity. For the application for the global south, it should be as cheap as we can possibly make it, and it should work only in the sunlight, so it shouldn't work when it's being worn. Okay, inherently it needs to be safe. Okay, so whilst I am a catalysis person, I'm a physical chemist, okay, I'm interested in material science, I'm certainly not au fait with antimicrobial and microbiological work. So in collaboration with two colleagues over in our pharmacy department, so Dr. Mike Pascoe and Professor Jean-Yves Maillard, okay, we actually made a proposal and put a proposal into this call. Okay, and we were successful in securing funding. And what I'm going to do now is I've just got a couple of slides just showing our key results. Okay, so this is just a little cartoon of our setup. Okay, so if we look at the top left here, we have a light source that's irradiating a solution. So these are solution tests, and in this beaker, we have our photoactive compound, our photocatalyst, and bacteria. And what we do is we irradiate this with light, and we measure the remediation of the bacteria as a function of time, which is what this graph here is showing. And this line here where we have green at the top and red at the bottom at 99.9, which is actually a 3 log reduction. Okay, this is the activity of sort of household cleaners, so anything that you use to clean the kitchen. Okay, generally kills 99.9% of bacteria. So that was kind of our baseline, but what we'd be looking at is a much bigger reduction than that. And our target really is this 5 log, which is 99.999% reduction. And we evaluated 3 different photocatalysts, and the data is shown here. And all 3 of those catalysts showed excellent remediation activity of the E. coli after about 60 minutes. Okay, and this data at the bottom in the red zone, so this is the bacteria in just the presence of light, okay, without the photocatalyst, and also the dark reactions as well, and we can see that there's no activity there. Okay, so no activity are reduced in the dark, and no E. coli are reduced in just the presence of light. You need the photocatalyst and the light to see any remediation activity. Okay, and these wells are some destaining tests that we did. So each of these wells were filled with a small square of our best photocatalyst that had been impregnated onto a cotton square. We have an orange dye on the top, and then we put the light source above it. Okay, we measure how much of that chromophore within the dye is reduced over a certain amount of time, so 15 minutes. So this orange one here, this is the control. So this has no photo catalyst on it, and you can see that the solution retains its orange color. And also, if you remove the sample of the photocatalyst, that's also remains orange. Okay, and this one here is our best photocatalyst, and all of the dye has gone out of the solution, but also out of the fabric. So we're very, very happy. Unfortunately, I can't talk in any more detail about what the catalysts are and the steps that have been involved, because this is an active grant. We were successful in getting the funding, and we are literally just writing the follow-on grant now. Unfortunately, I'm not able to divulge any more on that. Okay, so where is the future of cleaning with air? Okay, as I just mentioned, so the Bill and Melinda Gates Foundation actually invited, when we showed them the progress that we'd made on this, they invited us to submit a follow-on grant, which we aim to be across 2 years. And this is to a little bit of further research and development, but also to study the feasibility and potential of doing field trials to get these products out where they're needed. We're also successful in securing some seed corn funding from UKRI for an interdisciplinary doctoral training hub. Okay, so this is money that brings colleagues from multiple schools and multiple colleges together on this problem, and to see how we can valorize and look at sort of further valorizing this idea of, do you actually need water to clean? And if you do have water, can we do cleaning more effectively? And then that will lead on to a full Centre for Doctoral Training application, which is funded for UKRI, and we're expecting the call, I think, around about November this year, and that will be for about £2 or £3 million. And also we can think about potential other applications for this. So I originally thought about this type of technology when I had my first child in 2014, and was pretty horrified by the amount of nappies that we were using and the amount of washing we did switch to reusables we were doing. But also you can think about uses in potentially in sportswear for things like tents. If anyone's had the misfortune of putting away a tent that you think is dry, and then when you get it back out again, you realise it wasn't and it's gone mouldy, you can think about perhaps having a treatment on that to keep it clean. And also in clothing generally. So anything that reduces the washing burden and reduces the amount of water that we need to use during a washing process would also be very good. Okay. Okay, that's it from me. I'm very happy to take any questions in the Q&A. Thank you very much for listening.
Great, many thanks both. Thank you for that really interesting and urgent call for what, Duncan, you referred to at the beginning as roots out of what might very well, if we do nothing, be a very dark future, and your emphasis on the complexity of roots out of net zero, and that as yet unmapped space that you refer to as a terra incognita, the things I have yet to be found, and your presentation, both of you, details one of those things. It is a space of possibility still, but we need to fill it quite urgently. And your emphasis also on the fact that there's no one silver bullet. It's a portfolio of solutions, and partnership working and translational working is key. And then Jenny, your striking presentation on Cardiff University's research to contribute to these solutions, and cleaning with light and air. It just sounds unbelievable. Cleaning with light and air. I'm going to start with some pre-submitted questions, and some other questions are coming in thick and fast. A question here about the range, if you like, of areas of research that impinge on or contribute in some way towards the carbon net zero problem. I mean, you've detailed ways in which you were collaborating, Jenny, with people from pharmacy, colleagues from pharmacy. Could either of you, both of you, say something about that range of disciplines in which the carbon issue is being tackled at Cardiff?
Shall I start? I mean, I think there's such a broad range of activity. I'd hope there'd be future webinars where we can highlight some of the other areas, but three I would maybe highlight just to give a sense of the breadth. I think one is work from the School of Engineering led by Agustin Medina Valera, using ammonia as an energy vector. One of the problems, of course, with things like wind power is what happens when it's not windy. How do you have the surplus energy when it is windy and store that? And ammonia turns out to be a very interesting material for storing that. I think to contrast that with work in the Welsh School of Architecture, they've long been pioneers in sustainable built environment, and the work of Joe Patterson looking at sustainable housing, but I think in particular retrofitting the existing housing stock to make it more sustainable. So not sort of brand new eco-build housing, actually taking the existing housing stock and making that sustainable. And finally, underpinning so many things, that the work in the Centre for Climate Change and Social Transformations, CAST, so a social sciences team, looking at net zero futures and the human perceptions of those, how people embrace new technologies and work with new technologies. And I think, you know, that's so important for all of the physical sciences to work alongside those people.
Yeah. Jenny?
Okay, and just following up from that, in terms of the Gates work that we've been doing, I think the reason we were successful with that is that we recognise we can't be experts at everything, right? So it's like, I knew I can't do the microbiology, so it was very, very important to have those very close collaborators in pharmacy in order to do that. And certainly in terms of when we want to think about getting the product into the local communities, we can't just turn up in a village as sort of physical scientists and say, we want to give you these products. There's certainly social science aspects to that as well. And I think having all of that expertise together is when you can actually make particularly good advances. And I do think that it was key to our success was having all of that from the start for the bid. So.
Thank you. Some quick fire questions. I'll begin with you, Jenny, if I may. Brilliant question. It's a very, very direct one. Does the UK weather limit your research?
So not even just the UK weather, but the Welsh weather doesn't know. So the best material we've actually tested on the roof of the pharmacy building, and we still see the same activity that we do in the lab, solar simulated situations. So, and that was on a pretty rainy day as well. So no. The UV index tends to be higher in the global south as well.
Yeah, of course. Duncan, a comment, surely zero emissions is an impossibility.
Yeah, I think it is. Yeah, I mean, I think, you know, that was maybe my point, that there are two extremes. The reality's got to be in the middle. I mean, even, you know, in 50 years time, 100 years time, we have nuclear fusion to provide as much clean energy as we want. If we still want to use cement, that the chemistry of that process emits molecules of carbon dioxide. So we will always have some emissions, which is why, you know, we need to develop the carbon capture technology alongside this.
Yeah. A question about how we take our findings from the lab stage, from that lab level, which you've just profiled, out into the real world. We've been talking about translational research, you know, collaborations with industry, but what does that actually mean? What are the processes and timescales?
Shall I start again? I mean, I think that there's no one answer to that. It depends on the technology. Using the fuels technology I talked about, well, you know, a world scale petrochemical plant is going to cost several £100 million, possibly even billions of pounds to build. And so you need to work with organisations that have the capitalisation to be able to build at that scale. So that basically means working with industry partners in that area and co-developing with them. The sort of timescales for that, probably 5 to 10 years. You know, the petrochemical industry exists, so we know how to do the engineering, albeit that there's still a huge amount of work to do with that. But at that scale, you need to partner with industry. Different technologies, though, actually the route to commercialization there is through maybe startup companies and much sort of smaller scale operations. And I think this is where sort of even individual investors can really move the dial here in terms of being able to take technology from the lab into real application. So there's a whole range.
Thanks, Duncan. Jenny, is there a carbon footprint for the very catalysts that are meant to solve the issue?
Yes, so there will be. So I can't talk a lot about the catalyst one. It is a consideration that we have when we're screening materials, and we have a lot of things that we've tried. Yes, there is, and we need to perform life cycle analysis and these sorts of things to kind of figure out, you know, where the emissions are and stuff. It isn't, unfortunately, it isn't a one, but we expect the carbon emissions to be far less than those used traditional washing technologies.
Yeah. Duncan, you flashed up an image of a field and biodiversity, biofuels. That's how that first part of the presentation began. What are the challenges with actually growing biofuels?
Yeah, well, I mean, multiple challenges, and to be honest, you know, the UK is arguably not the right region to be growing crops for biofuels. You need areas where I guess the agriculture can be intensified and where much sugar-rich crops can be grown. I think there's really interesting developments in terms of the crops that are used here, and I think emerging crops such as energy grasses that can be grown in more marginal environments that can't otherwise be cultivated. Of course, there are still questions about biodiversity, and this needs to be done very carefully. But I think with the right crops in the right regions, it can at least be part of the solution. Yeah.
Jenny, funding. You mentioned the Gates Foundation. That's where your original funding, initial funding, and follow-on funding is from. Where else might it come from, or does it come from, and where else might in the future might it come from? As you know, it's Duncan said at the beginning, there's no argument that this needs to be done. What are the sources?
Yes, so certainly, so I would hope we are literally just writing that follow-on, so I have everything crossed at that's successful. So I think what we would think about doing is obviously for the humanitarian use that this would be and technology that would be used for that menstrual health sort of application. But then there is possibility to valorize this, and if we do submit some and we have intellectual property and we patent it, there's potential to license that. We can do some market research to figure out what are the sectors that we might not have thought of, might find it of use. So I think we would probably go down that sort of thing. In terms of traditional sort of research council, this doesn't really fit, I guess, perhaps with their funding. So having an idea of what the end users, what the the kind of companies that could use and valorize this technology would be how we would go with that.
Yeah. Thanks, Duncan. The institute, the Net Zero Innovation Institute, newly founded. Will it be influencing? Could it influence government policy? I mean, it can influence material change. What's the policy side of this and the policy possibilities of this research?
Yeah, I mean, I think I'd say inform policy rather than influence policy. Yeah. I think that our role is to provide the best possible evidence and to the data is required, and to provide expert opinion, and to provide maybe a roadmap of the technologies that are coming along. And then it's the role for the politicians to make decisions on how that's deployed with other things in the round. But absolutely, it's part of our remit to inform policy. And I think being in Wales offers something distinctive here. I think Wales as a nation, I would argue, is very well placed to play a real leading role in net zero. I think with the range of industries and agriculture we have, in a way we could be the pilot study for the rest of the UK and the rest of the world in reaching net zero. And they're the arguments that I would be taking to government.
That's a really good point about the Welsh context. Many members of the audience will know what the REF is. The Research Excellence Framework has just been concluded in 2021, and Cardiff University did very, very well as far as the impactfulness of the research is concerned. Extremely well, and that was often based on, as Duncan said, our ability to influence policy. Once one's research influences policy, that's a very, very clear material consequence of good research and persuasive research. Jenny, we've got some wonderful comments here and compliments to you and Duncan and to the university on bringing this issue down to, if you like, a personal level and a household, your word, household level. That's it begins at home, doesn't it?
Yeah, absolutely. Yeah, and I think that a lot of the research that I've done or that I'm doing is kind of that immediate sort of personal sort of application. We've worked sort of with industry before, but it's certainly since I've had children, to be honest, it's like, what can we do as individuals that can kind of really make a difference, and the potential of the product, based on the data we have, could make a real impactful difference on the lives of these people that really need this technology. So yeah, it's something that I do feel does drive me a little bit, is seeing how we can make people's lives better.
Yeah. There's a question here about timescale. Speaking of time, we've got 5 minutes left. I'll read the comment. I feel those solutions are innovative. They do strike us as extremely innovative, but are they more part of a future solution rather than solutions to immediate problems?
Yeah, so certainly, so the definition that I took is sort of trying to take emissions down to zero. So if we can remove the need for the emissions associated with water or reduce them, that's going a little way towards that. And also it's that generation of a post net zero technology as well, when you don't want to be reliant on sort of converting CO2 or even using CO2 as a feedstock. Let's try and move away a little bit perhaps from that and think about how we can live in this hopefully post net zero world.
Yeah.
Duncan has any other thoughts on?
Yeah, no, absolutely. Look, I mean, the target for net zero is 2050. There are things we can be doing now that are, and if the things we're doing now have to be technology which is available now. Yeah. The closer we get to 2050, then you would hope the bits that we need to decarbonize then are the bits that are more difficult to decarbonize. But to do that, we need to start to develop the technologies now. So absolutely, these are technologies for the future. But if we want them in the future, we have to start that development right away, or it's too late.
Yeah. Thank you. Two final questions, one technical and one more cultural. Hydrogen, Duncan, as a possible fuel tomorrow. You mentioned ammonia. There are problems with both of those as parts of any solution. Am I right? Absolutely.
Yeah. Hydrogen will certainly be part of the solution. Ammonia will be. Electrification will be. I'd draw attention to the energy systems group in engineering. I think to look at these in isolation is kind of not always helpful. You need to look at this as a system. And that is that, the parts that need hydrogen, the parts that need electricity, where ammonia comes in. And I think that more holistic approach, to a systems approach to this is something where we have a strength of research in Cardiff, but is going to be hugely important in solving these problems.
Thank you. Final question, Jenny. Your day job, you excel at it. You're a distinguished researcher. You're winning these research grants, and as you said, fingers crossed with follow-on funding. Do you get frustrated with the speed, the rate of organisational change? And I'm not just talking about Cardiff here, which I think is on the money, but we all buy into it, but it's a huge tanker to turn, isn't it?
It is, and it's something that, again, I will always kind of bring back to the research that we're doing with the Gates Foundation. It's something that we're very conscious of there as well, and this awareness that we need to do a degree of education to kind of get acceptance for these sorts of new technologies and these new products and things in the communities where they're going to be used. So one of the big things that we're looking at, thinking about for the follow-on, is actually having local champions and local collaborators and enabling the community to make these things themselves, but with that education as well. And that, yeah, so yes, absolutely.
That is a good place to end. We're out of time. Duncan and Jenny, thank you so much for joining us. And I also want to thank our audience for those questions. Hope you found it interesting and urgent. If we didn't get a chance to answer your question, I think we did a good job of trying to muster responses to most of them. We'll follow up with you directly. You will receive an email in the next couple of days, actually, with a copy of the recording, as I said at the top, and links to register for forthcoming events. And on that issue, our next event taking place on Tuesday, the 15th of November, and we'll hear about current research into how mental health can be improved through genomics, interestingly. Hope you can join us for that. If anyone watching would like to get involved in Cardiff University research, volunteering time to help our students, help us to fundraise for our research, please follow the link in the comments box that I can see is being flashed up as I speak. Diolch o galon I chi am fynychu heno. Wy'n diolchgar iawn. Gobeithio bod chi wedi cael blas a bydd o'r cyflwyniad a'r drafodaeth. Hwyl fawr i chi. Thank you so much for attending again. Duncan, Jenny, thank you so much.